Okay, so good morning, good afternoon. I'm Mirko Baggio, Director of Business Development for Zapi Group. I'd like to welcome you to this session. Please remember that this session is also being recorded and will be available to watch on demand following this session. If you have any questions, please add them in the Q&A session. You can find the tab on the right of your screen. Note that your question will be sent privately. With that, I would like to introduce our speakers. I'd like to welcome Alexander Stening and Robert Grahn from Cascade Drives, who will be speaking today about electrifying linear motion. Cascade Drives is working in the same environment and market as Zapi Group. For this reason, we have many common projects. Welcome, Robert and Alexander. Please take it away.
Thank you, Mirko.
Thank you.
Welcome, everyone. Good morning and good evening. Yeah, so my name is Robert Grahn. I'm head of the software and system electronics department at Cascade Drives. And with me today, I have Dr. Alexander Stening.
Yeah, Alexander Stening, electrical engineer at Cascade Drives.
Good. So I think that is kind of a good start to understand a bit what we do at Cascade Drives. So what we normally say is that we kind of take the next step in electrifying the future. As you've already heard from several speakers before, I think Evelix made an excellent presentation of considerations and details selection criteria before us. So we're kind of gonna add on top of that. So as most of you know already, we are seeing kind of the next step of electrification. What we also see is that stationary equipment that traditionally have been hydraulics are now moving towards more sustainable solutions. Alexander will come into details of such type of products. And what we bring to the market is key technology, a key subsystem for power steering, lifting, tilting, tipping, but also for pumping and whatever crushing needs the market have. As we saw previously, there are a lot of considerations to take when moving to current technologies like ball screw or roller screw or staying with hydraulics. There are a lot of limitations in terms of the load and speed capacity. Also, there is a lot of limitations on the shock load capabilities, especially when electrifying the heavy machinery with the heavy hydraulics. Of course, on the hydraulic side, our kind of traditional competition on the market is having, of course, also some limitations on speed and load. You can have either. Also, high operating costs with low efficiency on hydraulic side, where we basically cover a bit of a new piece of the puzzle. And just as Evelix mentioned in the previous presentation, the maintenance cost is generally a lot lower with a electromechanical solution rather than a complex hydraulic system. So, Alexander.
Thank you, Robert. Compared to traditional rack and pinion solution, we use multiple pinions to drive a double-sided rack. Each of these pinions are connected to a CD gear, which takes us to the next slide. The maximum force that can be transferred by a rack and pinion, a traditional one, is a function of the size of its components. This increases the system inertia. By using multiple pinions with a smaller diameter, we can increase the force and we can still maintain a low inertia. An over-defined system is avoided thanks to the torsional flexing properties of the CD gear, ensuring an equal load distribution between the pinions. I think next slide will show some features of the CD gear. The built-in pinion flex makes CD gear resistant to impulse shock loads. So thanks to this torsional flexing property of the gear, we can handle shock loads. So what we get is a small footprint, a low inertia, no backlash, and increased gear life. We can reduce the backlash since we can pre-tension the gears in different directions since we use multiple pinion system. Yes, I think we can take the next slide, Robert. We are continuously working on the development of the CD gear technology with main focus on fatigue testing, including effects of the presence of high temperatures and oil. Dynamic loads are important part here for fatigue testing, as well as for the development of sufficient models relying on the stiffness. We have damping and non-linearity effects in the CD gear as well, important part of the modeling task here. The graph shows here a typical response of the CD gear when we take a torque step on the motor side here. In the middle graph, you can see how the torsional flex can react depending on how we design it when we take a torque step. So this is the key feature here of our actuator technology, I would say, the CD gear technology, where we can add several pinions to one double-sided rack. Yes, I think this concludes this slide.
Yeah, I think it gives a good idea of the patented technology that can realize this product. Telling a bit about kind of our current product platform. So the company is built upon this mechanical gearbox with this pinion torsion flex unit technology. As customers today, they can choose multiple different ways of configuring our product. It's possible to choose different rack diameters, which is about equal to the hydraulic piston diameter in terms of force. And we can also choose to either kind of center mount or mount the housing in the middle, so we get like a dual action system. But we also can do it more like a traditional hydraulic system with a tube end. And on the motor side, there are multiple different configurations where you can stack the motor on top of the gearbox or straight into the gearbox or through bevel gears. Or yeah, it's very flexible, of course. is the idea. We are working across all industries, more or less. So wherever there are lifting, tipping, steering needs, we are working there. On the industrial side, we have multiple water pumps and gas compressor customers. On the material handling side, we have both customers where we're working with steering, because this is very suitable to electrify steering. But also, as Alexander will show, we have done several customer projects on lifting, etc. And then on-road electric power steering is a separate segment due to its really stringent safety and security requirements. Looking at the specific market segment of power steering, the company have gone from being more of a mechanical component supplier, realizing that OEMs, they are not interested, or at least not willing to really deep dive into the deepest parts of technology, like controlling the motor torque, etc. So one major part of the business for cascade drives is to do integration, and especially for power steering, where we develop all types of application software on top of controllers. This could be either directly into in motion inverters, for example, which we have done in several projects, more for the off-road business, but also in controllers for the on-road market. What we did maybe not mention, Alexander, is that we can measure the linear position and the linear speed by just adding encoders directly to the rack side of the system. And by this, we have an extremely good precision, control precision of the system.
True.
So I will just show a few kind of configurations that might spring some ideas of how our system can be used. So this is specifically for steering, but hopefully you will get a grasp what could be done in kind of other applications. So today we have several bus installations where we basically just remove the hydraulic pitman arm hydraulic system and just adding our electromechanical steering system with a manual input shaft from a steering wheel. Then we just multiply based on vehicle speed the driver applied torque to create kind of any type of steering behavior the customer wish to have. So this is our assist product. It can also be center mounted. This is a bit of a bigger step, just as Evelix and other electromechanical product suppliers are facing. This is always a challenge due to the tradition of some other hydraulic solution. But we are seeing more and more adaptation of this way of mounting our product, since it gives a lot of benefits. Beyond just being electromechanical manual input shaft assist system, this can easily be adapted at a later stage to something more like a steer-by-wire product. So we are free to alter the motor setup We can have dual motors, dual controllers to achieve a fully redundant steer-by-wire product. For off-road fenced-off areas, this system can, of course, be a lot more simplified if safety levels doesn't have to be kind of that high. Just to give a brief understanding of how like a really big heavy axle could look like. So this is the 70 millimeter rack diameter gearbox we have. So this is a really, really heavy AGV axle. And the reason for going to an electromechanical steering, in this case, for example, is the fact that the navigation system needs higher precision in steering and less uncertainties in whether the actual steering has occurred to the extent requested. Also, we can have extremely high steering speeds here due to the gearing of the gearbox. So we have multiple installations. This is going to be an autonomous bus at a point. So just to give you a small brief idea of how this system can be integrated and how it behaves. So customers are using this in speed control, linear speed control, or linear position control. We can flexibly integrate any type of control needs from the customers. So over to you, Alex.
Thank you, Robert. This is an example of a marine loading arm. We have successfully designed, delivered, and certified actuators for such a marine loading arm. Why is this of interest? It's, of course, to avoid hydraulic leakage, reduce maintenance cost, improve controllability, and to reduce the power consumption. Our linear actuator is back drivable, so during an emergency release from the ship, it can handle all the things that happen there. The crane shown on the right here is our first certified crane installation. Something more to say here?
Sure, I could add. So this customer normally have hydraulic pistons here, and are bound to like a man-controlled motion, and only per function. What we can realize, thanks to our precision control of each function, is a very, very high level of automation. So this customer can basically automate a lot of different motion controls to go back to storm lock modes. This system can also compensate for drag, wind drag, things that were completely impossible or extremely costly, at least, to realize with the previous hydraulic system. So that that can be interesting to know, I think.
Yes, we also supply actuators to replace the hydraulics in high pressure pumps. This is a quite interesting segment according to me. These are typically used for hot isostatic pressing, water jet cutting, and also food processing. We're working here under very high loads and relatively high speeds, I would say, compared to the short stroke that is usually used here. And now we have also seen an increased interest in pumps for the manufacturing of solid-state batteries. So here we see a future potential. I will show you some details regarding a linear water jet intensifier. This is a schematic overview over a hydraulic linear water jet intensifier. The ratings of such an intensifier is typically within 20 to 100 kilowatts. We have been working a lot around 37 kilowatt. The water pressure is usually around 4,000 bar for the water jet intensifier, with a nozzle diameter of 0.1 to 0.5 millimeters. So this is commonly used to cut different types of materials. Here you see a hydraulic cylinder used to compress the water through plungers with a relatively small diameter. So you can, at the end of each stroke, you achieve these 4,000 bars when operating at full speed, I would say. So this requires a hydraulic pump, usually driven by an electrical motor. So this type of linear motion makes this process very suitable for us to go in with an electromechanical linear actuator for a direct replacement here of the hydraulics. I think next slide here shows an example of such an intensifier. It provides a higher system efficiency and an increased controllability with a much higher endpoint accuracy, I would say. What we have seen so far is an accuracy below 0.1 millimeter. And we can vary the stroke length here, which I believe for future installations can be a benefit. By extending the stroke here, we would increase the system efficiency, I guess. I think you can move to the next slide, Robert. Just some... this is an example of a typical requested motion profile for such an intensifier. During the design stage, some important factors to consider are, of course, the load, the motor inertia, the gear ratio, and the motor torque utilization, and the characteristics of the CD gear here. We can use stiffer materials as the compressible elements, for example, since we are working at quite high loads. The graph at the bottom there shows the position as a function of time. And you can see that for this stroke, it takes 0.8 seconds roughly, going from the left side to the right side. So it's a fairly fast process since the motor is going up to the design speed and down to 0 again within this time. I think we can take the next slide. Looking at the torque required to drive this process, it's derived from the accelerating torque and the load torque. And at such high pressure levels as 4,000 bar, the water is compressed by somewhere around 10%. At the end of each stroke, we will have some dead volume, non-acting volume after the plunger of the intensifier. This acts like a spring. So the kinetic energy stored mainly in the motor during the motion is transferred into energy as pressurized water at the end of a stroke. This energy is then used to accelerate the movement again at the beginning of the next stroke. So the torque required during acceleration and deceleration, it is reduced. The graphs here show from the top accelerating torque, followed by load torque, and then at the bottom, the resulting required torque by the motor. This is, of course, a simulated curve here, but it has been verified as far as we can through measurements on existing systems. But I think it shows how we can design the system in terms of gear ratio and motor selection and so towards the load to get as smooth motion as possible. So looking into the next slide, the deceleration process for a motor inverter setup usually requires a braking resistor or a regenerative feature of the motor drive. This can be avoided here in the linear intensifier by, as I said, choosing the inertia and using this energy stored in the dead volume with a sufficiently chosen gear ratio. So in this case, power is only transferred to the load. This is seen in the bottom graph here, showing the transferred power from the motor into the mechanical gearbox. So you can see that we have no negative power here. An example of how we can design the actuator towards such an application. So moving on, Robert. Measurements on one of our setups here confirmed a system efficiency of 87%. Looking at the different components within our actuator system, the electrical motor and drive efficiency was 92%, and the efficiency of the mechanical actuator was 95% in this case. These measurements also show the positioning error less than 0.1 millimeter. As you see at the bottom graph here, we operate around 4,000 bars. On a complete system level, this could mean a loss reduction of up to 40% compared to standard hydraulic water jet intensifier, somewhat depending, of course, of this hydraulic setup. Now we will move forward and show something from the material handling segment. The electrical forklift is a good example where several hydraulic functions can be replaced. This could be the lifting function, of course, here for the forklift, the tilt and the spread function, and also the power steering, requiring quite some force in this case. This is an example coming up here for a 16-ton forklift lifting actuator solution, intended for a 16-ton forklift truck, I should say. This is one of our first installations, made quite some years ago now, for testing of our larger actuators, the 108P configuration, where we used a lifting mast from a forklift truck to make a test setup. At this point, we did not have access to a high voltage battery, so we had to rely on the electrical grid that was available. In this case, it was a 32 amps three-phase source. So this explains the relatively low lifting speeds that we show in the graphs here. You see on the upper left graph here, we show the position of the load as a function of time when we load the forklift with 16 ton. To the right, you have the power consumption as a function of time. And at the bottom right, you can see the energy consumption during the entire cycle. So first you see that we consume a lot of energy to lift this load, and we lower it to the starting position again. And when we reach this position, we have recovered 60% of the energy consumed during the lifting process. And I think on the next slide here, we show also we developed a steering actuator for this 16-ton truck. 47 kilonewton rear axle steering. This forklift solution has not yet been realized on a truck, so we will move forward to a similar solution that was placed and tested on the vehicle. Together with Kalmar, we had the opportunity to electrify the lifting device of an empty container handler with the listed requirements. Lifting of 9-ton containers up to a height of 18 meters. With this duplex mast, this means an actuator stroke of 9 meters. So it was a bit of a challenge to get these racks manufactured and delivered within the project time schedule. But we managed to do that. And we have included here a mechanical holding brake for safety reasons. We increased the standard lifting speed of such a vehicle is 0.6 meters per second, up and down. But with this solution, we can produce 0.8 meters per second. Including the weight of the mast, each actuator was designed here to 230 kilonewton. And here we operate towards a high voltage battery. And now I think we have a video the result. Here you see some results from the testing of this vehicle. We did a lot of testing with different container weights and lifting speeds. The measured battery voltage and current was used to calculate the energy consumed during lifting and also to calculate the energy recovered when lowering the load. An example of a lifting cycle is presented on the left, showing the container position and the consumed energy as a function of time. We lift here up to almost 15 meters. The full lifting height is 18 meters for this vehicle. As can be seen, a large amount of the energy consumed during lifting is recovered here when we lower the load. The amount of recovered energy is shown on the right as a percentage of the energy consumed during lifting, where the x-axis indicate the container weight in tons, and the y-axis shows the container speed in meter per second. I think this heat map here reminds us of the image that Robert showed earlier in the presentation, where we see that we have a good area with high speed and high load, where we can operate very efficiently. At full speed and full load, for this case, 65% of the energy consumed during lifting is recovered when lowering the load back to the starting position. And this, should we remember, includes the losses in the mechanical mast here. Unfortunately, we had no possibility to separate the losses. So the mast losses are included in this figure. We should remember this. So it includes electrical drive, mechanical actuator, and the mast. On the next slide here, we see the main findings as stated by Kalmar in a press release. They state that they increased the lifting and lowering speed by 30%, more than 60% energy savings in lifting and lowering functions, which means for a typical driving cycle, a 20% reduction of the total vehicle energy consumption. This was measured when they operated the vehicle for a typical cycle and measured the amount of consumed diesel. Because the high voltage battery was not connected to the propulsion system, it was not an electrified vehicle. Today, we have an ongoing project where we electrify the boom of an excavator. It's very similar. in the material handling segment. We have seen some trends. When replacing the hydraulic system in various applications, we have noticed that there is a market gap. For example, high voltage, low power auxiliary drives is something we would like to see more of. Integrated inverter motor units, especially for low power levels. 48-volt control systems. And we also see an increasing interest in off-grid solutions for fixed equipment, such as cranes, where battery and solar solutions are interesting, providing a quick deployment. We also see an increasing trend for portable high-pressure pumps with low maintenance.
I think maybe coming back to the market gaps, maybe even stepping back even a bit further into our presentation. You should all remember that all of these applications and everything is basically drop-in solutions. So in basically not a single case has there been any optimization of the geometries or anything. So we are basically designing our gearbox and actuator based on the current platform that these OEMs have. So just as Alexander said, increasing the stroke, for example, in pumps, or alternating the geometry of, for example, excavators, or especially wheel loaders that have extremely high rack forces required, but very low speeds required. That's, for example, a product where longer lever arms with higher top speeds would be a better solution for electrification, for example. So that's kind of some insights that we believe the OEMs will face as well as they are starting to look at electromechanical solutions also for the really heavy, powerful hydraulics that they eventually will like to remove. Hood lifting, rear view mirror tilting, those types of function doesn't have that kind of requirements, of course. And then coming back to the market gaps, as Alexander say, most of the kind of electrification 2.0 step is not of the magnitude of a propulsion system. Those systems are way too powerful for most auxiliary functionality that we have faced so far. So for example, we've looked at the SAPI HV2 high voltage, relatively low power auxiliary system for some customer integrations. Really else, I would say the 48-volt trend is definitely going to come. We see a lot of on-road customers that are requesting kind of a common electrical architecture, both for controls and the auxiliary drive itself. So I think that's going to be a crucial step that more should step into to kind of tag along on this 2.0 trend. So thanks a lot for listening in. This is where we round off today, but we are happy to answer any question, or for anyone being in the area of north of Stockholm, you're free to drop by. Thank you.
Yeah. Okay. Thank you, guys. Thank you, Alexander, for the very detailed and interesting presentation. So we have some questions from the audience. So first of all, how do you provide load protection similar to the use of a counterbalance load holding valve? I guess is the brake that you have shown already. I guess is to limit the falling down of the load. I guess the question.
Go ahead, Alex.
Yeah, it's a safety function if that is what you are meaning here. In case of a power loss, we have a normally closed brake.
Mm-hmm.
The control system, either we design the brake control or the customer deploy their own intelligence behind the brake control. So it all depends. Like, for example, in an excavator, we have some extent of understanding of how the application is used, but for the excavator, the customer, for example, like to have a non-locking system while operating the excavator, but as soon as the excavator is standing still for a certain amount of time, then we apply the brake and stop controlling the electric motor. And then as soon as the user is again using the function, it can be any kind of function, then just energize the electric motor and then release the brake. This is normally done within a few hundred milliseconds.
Okay, another question. Any aviation applications?
Any?
Aviation. Not so far.
Which means? I don't follow.
I guess rudder control or something like that.
Yeah, I guess to move the flap or what the part of the airplane that are normally moved by hydraulics.
Yeah. No, we have not stepped into any application. I think we have maybe not either attacked it from a sales perspective, to be honest. The level of homologation, certifications, etc., is extremely high, as we understand. So it might be in the next step. Also, since there's a big difference between hydraulics and our system, as I think is understood by now. So hydraulics, you produce the power somewhere else, and then you have hoses, while we have the whole gearbox and the motor itself on the actuating motion machine. So this increases the weight where we produce the rack force. So maybe with lightweight design, maybe 3D printed, metal 3D printing, etc. Magnesium, titanium, maybe that could work out. And it would be interesting for space applications as well.
Yeah, I have a couple of questions from my side. Since for my job, I am really interested in new applications and new business. So the first question is related to the on-road applications, so truck and bus, mainly for steering. And we know how many challenges you have in this market due to the functional safety ISO 26262. So what is really the advantage for the OEM to move to the mechanical steering instead to keep the hydraulic solution? Is that the power consumption?
So this is kind of a multifold Q&A, I think. But one aspect is definitely energy consumption. If you have, for example, a long haul truck that is traditionally not steering much, then we actually consume a lot less power, at least compared to a traditional system with a hydraulic pump on the motor, like the combustion engine. Maybe not so much if you have an optimized hydraulic system. But maybe moving to the next step when we are talking about automation is basically, as we believe at least, impossible to ensure that you actually have the hydraulic force you need to do the motion itself. So you can have as many motors and as many hydraulic pumps as you wish, but you will have to add a very, very complex measurement system to know for sure that the hydraulic liquid or fluid is actually reaching the piston or the twisting motion.
Okay.
So a lot of customers are coming to us with burnt up electronics because they've been trying to work against broken hydraulics.
Okay. Yeah. Okay, it's clear. And the other question is related to the industrial application, like the water jet intensifier. So I understood that it's possible to use your linear actuators, but I didn't catch what is the advantage instead of the existing solution.
Mainly energy efficiency for the pumps.
Okay.
They are working quite fast under a high load. And as I understand, in some cases, more or less continuous operation.
Okay.
So energy savings around 30 to 40% there. That's the main driver, I would say. Of course, we could also, if we can increase the stroke length, we could pump more medium under a certain time.
Yeah.
So like
Since the turning points here are actually lowering the efficiency of the installation.
Yeah. And I think what you said, Robert, before, we are, let's say, just in the beginning. So we are trying to convert existing solutions in electromechanical. But if you have, let's say, a design made on electromechanical solution, maybe you can get even better results.
Yes. I think that's what we see basically. Correct me if I'm wrong, Alexander, but so far we have not seen one single application that is like already optimized for our solution. Like it works perfectly fine, and it gives actually to me quite astonishing results. Like we see 30% measured energy reduction for these pumps, and that's just one pump, and there are hundreds of thousands of these pumps. So maybe it really make a huge difference in energy consumption. Really big. But we could take like yet another step. That would of course be to just increase stroke, increase the length of lever arms to have like allow a bit more speed for the torque or force. Just be able to exchange more hydraulics for electromechanics. Then we also add functionality, like for example these pumps. We can alter the pump speed during a stroke, which is impossible to do with the hydraulics they have today. Of course, you can do very complex hydraulics as well, but it's really easy to control in our case.
Okay, then finally we have another question. Have you done a one-to-one cost comparison to a traditional hydraulic solution, like for steering or lifting? I think is meaning probably TCO, but yeah.
Yeah, so
I know the answer, but
so we have done total cost of ownership calculations. If you're buying a one-off, very complex system of ours, of course it's going to be costly. But the total cost of ownership is looking like is tipping over for our benefit, at least when we've been looking at small AGVs, for example, like big AGVs with small volumes. So even in those cases, the total cost of ownership is looking good. And there is no strange technology inside. I mean, it's a gearbox. So if you go to a Volkswagen dealer and purchase some off-the-shelf gearbox, it's going to be extremely cheap. And we make our gearbox even simpler. So in most cases, unless you need extremely quiet machines, then we have straight cut gears, for example, or belt drives. So it's kind of basic technology. So.
I guess that today, I mean, hydraulic, they have so big volumes that they have so let's say, so low prices that is impossible to compete. But
Unfair competition in that sense.
as you said, when technology will be established, that there is room to get winning total cost of ownership.
There is no silver bullet, of course, as you saw both in the graph Alexander was presenting and what I showed in the beginning. There are other technologies that are more suitable for certain things, but we are definitely reaching into where hydraulics were thought to be the only solution.
Yeah. Okay. So I don't see any more questions. So I think we are on time. So thank you again for your participation. And yeah, talk to you soon. Have a nice evening.
Yeah,
Thank you.
likewise.
Thank you.
Have a good one. Thank you.
Yeah. Bye.
Bye.